Hello everybody. So, we continue with our discussions on the flow pattern based modeling approach which we had started in the last class. In the last class, after discussing the drift flux model, after discussing the homogeneous flow model, then we went over to discuss the drift flux model. Now, what the drift flux model basically does, it incorporates some particular constants which have been derived considering the distribution of the two phases in the conduit. So, therefore, it incorporates different constants in the equations if the flow is bubbly or if the flow is slug, and based on those particular constants it tries to predict the hydrodynamics of the different flow patterns. Now, this was definitely a good approach, but more specifically if one considers the exact distribution of the two phases and then tries to model it from the basic mass momentum equations, then it is expected to give a much better representation or much realistic representation of the physical phenomena. So, in this class we will be discussing one such analysis for the slug flow pattern, keeping in view that the slug flow pattern is the most widely occurring flow pattern in microchannels, and as we have already discussed. Now, in macro channels also there have been several attempts to model the slug flow pattern, and the usual approach of modeling is the unit cell approach. What is the approach? Let us see now. In this approach we assume that the flow is completely or perfectly intermittent or periodic, where the entire flow passage can be divided into unit cells, and each unit cell comprises of a liquid slug and a gas plug or a gas Taylor bubble. So, therefore, how can we imagine this? We can imagine the entire flow passage to be comprising of a large number of unit cells, and each unit cell comprising of one gas slug which is immersed in a liquid film and a liquid slug. In narrow passages we find that the liquid slugs are almost pure or they comprise of single phase liquid flow. So, naturally they can be modeled from single phase dynamics, and the Taylor bubble region is the two phase region where the gas plug and the liquid film which flows in the annular passage between the Taylor bubble and the pipe wall, it flows countercurrent to the Taylor bubble. So, therefore, this can be modeled by approximated the flow in the Taylor bubble region to be or to resemble the annular flow. So, therefore, the other assumptions which we make here is that the thickness of the liquid film is constant, which is quite a logical expression considering because the thickness of the liquid film, it becomes asymmetric. It is usually wider in the lower portion as compared to the upper portion, and this occurs primarily due to the effect of gravity. Now, since in microchannels there is a decreasing effect of gravity and an increasing effect of surface tension, so therefore, the assumption of axially symmetric gas slugs and constant thickness of the liquid film are justified. And naturally, the other assumption is the liquid film velocity is much less as compared to the velocity of the gas as well as the liquid slugs. And in addition, we find that in this particular case, therefore, the usual step of modeling is we try to find out the pressure gradient in the Taylor bubble region, we try to find out the pressure gradient in the liquid slug region, and in addition we consider another particular pressure gradient which occurs because the countercurrent flowing liquid film comes and meets the upward flowing or the forward flowing liquid slug, as a result of which some mixing and some turbulence results at the end of the Taylor bubble, which also should be contributing to the pressure drop of the entire slug unit. But this usually it is neglected under most of the circumstances. So, therefore, with this particular assumptions we start the modeling as I have already mentioned. So, as discussed, the frictional pressure gradient. I would again like to remind you that the pressure gradient, it is predominantly frictional for microchannels, and there is very less effect of orientation, since gravity is not very important in this particular case. So, therefore, the frictional pressure gradient, this is equal to this should comprise of the pressure gradient in the Taylor bubble region. This should comprise of the pressure gradient in the liquid slug region, and it should also comprise of the pressure gradient due to the drainage of the liquid film into the liquid slug at the Taylor bubble. And each pressure gradient, it should be multiplied with the relative lengths of the individual Taylor plugs and the Taylor slugs, isn't it? So, this is going to give you this particular complete expression is going to give you the total pressure gradient, the frictional pressure gradient, which occurs over unit cell, rather it occurs from here to here, which occurs over the unit cell of the slug flow pattern. Now, let us see how to evaluate, how we go about evaluating the individual pressure gradient terms. We naturally start with the simplest, the frictional pressure gradient in the liquid slug. Now, since just only liquid is flowing in this particular case, so naturally this can be evaluated from mere single phase fluid flow hydrodynamics, which gives the expression of frictional pressure gradient as rho L J L square by 2D, where naturally FLS, it is a function of the Reynolds number in the liquid slug, which is again a function of the Reynolds number, which can be defined as rho L JTP D by mu L, isn't it? So, therefore, sorry, I made a mistake, this should have been actually JTP square, because remember one thing, in the liquid slug region, the liquid is flowing over the entire cross section, therefore, it is flowing at the total mixture velocity in this particular case. So, therefore, in the slide I have represented it as J, but J in this case means the two phase volumetric flux. More specifically, I can refer to it as JTP. So, therefore, we find that the frictional pressure gradient in the liquid slug it can be obtained from single phase hydrodynamics, where the unknown FL, the friction factor in the liquid slug, can be expressed in terms of the Reynolds number, which is expressed in this particular way, and we already know from our single phase knowledge of single phase hydrodynamics that FLS equals to 64 by RELS for laminar flow and the Bloch's step equation for the turbulent flow, provided we have to remember that this equation is applicable provided we are considering the Darcy friction factor. Right. Now, again let me tell you that for most of the cases we neglect the pressure gradient due to the drainage portion, but in case someone wants to do a very accurate modeling, then this should be considered, and the person is advised to refer to the paper of Duckler and Hubbard, who have derived this particular expression considering the countercurrent motion and the relative velocity between the film as well as the liquid slug. Well, now we come to the modeling of the Taylor bubble portion. Now, for the Taylor bubble portion, what do we find? That firstly, I would like to mention that for macro systems, usually we notice that the frictional pressure gradient in the Taylor bubble region, it can be neglected because it is much smaller as compared to the frictional pressure gradient. It is usually much less as compared to the frictional pressure gradient in the liquid slug region, right. So, therefore, very frequently for macro systems, what is a conventional way or conventional approach is that the frictional pressure gradient for the entire unit cell, for the two phase slug flow, it is often approximated as the frictional pressure gradient in the liquid slug, it is better written as approximated, into 1 minus alpha, assuming that alpha is the void fraction and the entire gas flows as the Taylor bubble, and the liquid slugs are completely unaerated. So, naturally the portion, and also we neglect the liquid in the film as we assume it to be negligible as compared to the liquid in the slug. So, therefore, we assume that the entire 1 minus alpha portion of the liquid flows as slug, and accordingly the pressure gradient of the unit cell is approximated as 1 minus alpha times minus dP dz FLS. Now, although this is fine for macro systems as well as for mini channels, but the pressure gradient in the liquid, rather in the Taylor bubble region, it becomes significant for micro channels and also for mini channels for refrigerant flow, right. For these two cases, it becomes almost it becomes quite important for micro channels and also for mini channels for refrigerant flow. Because in this case we cannot completely neglect the gas velocity and density as compared to the liquid velocity and density. So, therefore, for micro channels and milli channels during refrigerant flow, this particular term has to be considered, otherwise we can neglect this. Now, in case we have to consider this term, then let us discuss how this term can be evaluated. Now, we know minus dP dz frictional Taylor bubble, this can be written down just like we have written down for the liquid slug region. In the same way, we can write it down for the Taylor bubble region, right. In the Taylor bubble region, then this is F at the interface between the bubble and the liquid film, rho g square u g minus u I whole square divided by 4 into the radius of the Taylor bubble or 2 diameter of the Taylor bubble. So, we have expressed the frictional pressure gradient arising due to the friction between the Taylor bubble and the liquid film. So, naturally it is a function of the interfacial friction factor and it is a function of the relative velocity between the bubble and the interface. Now, in this particular equation we find that u I is an unknown. So, next we try to find out, or rather we discuss how to find out u I, but before that I would like to mention that just like single phase dynamics as well as the hydrodynamics of the liquid slug region, in this case also F I, it is nothing but a function of RETB, where we can write down RETB, which is nothing but equal to the gas phase Reynolds number, that is equal to, in the same way, RTB into UTB minus UI divided by mu g, right. And remember one thing, I think I should not be using both the symbols, it will confuse you further. Remember one thing, since the entire gas flows as a Taylor bubble, so in this particular case UG equals to UTB. So, even if I use both the symbols, remember one thing, it is the velocity of the Taylor bubble and the gas phase velocity, the in situ velocity inside the conduit, they are identical, right. So, therefore, Fi can be determined from as a function of RETB. Again the same equations are applicable in this particular case as well, the same type of equations are applicable, and RTB, it is nothing but the radius of the Taylor bubble portion. Now, we come to discussing how to find out the interfacial velocity. Once we can find out this particular velocity, we can very easily calculate the frictional pressure gradient in the Taylor bubble region. Now, in order to find out UI, what do? We start from the basic momentum balance equation for the liquid film and the gas core. So, therefore, we first start by considering the Taylor bubble to be more or less approximated by the annular flow pattern. Okay. So, we assume that flow in the Taylor bubble region as ideal annular flow and we neglect effect of gravity. This is definitely justified for milli and micro channels. So, naturally, if we can neglect the effect of gravity, then the momentum equation for laminar flow of any particular fluid, it can be written down as minus dP dz plus mu by r ddr in cylindrical coordinates. This can definitely be written down provided we have neglected the effect of gravity. For any laminar flow, this is applicable provided we what I mean to say, this is equally applicable to the Taylor bubble region as well as in the liquid film region. Only the boundary conditions for solving this equation are going to be different for the two cases. Now, the general solution can be derived for both phases in laminar flow. How to derive it? We apply the no slip boundary condition at the wall and continuity, this is 1 and this is 2, continuity of velocity and shear stress at gas liquid interface. So, based on these two assumptions, we find that the general solution to this particular equation, which I have also mentioned here. So, therefore, the general solution is as I have given. This also I would like to write down so that you can follow it better. The general solution can be given as minus dP dz r square plus b ln r plus E. Now, this is highly applicable for both liquid film and Taylor bubble, provided the flow in both are laminar 1 and 2 fully developed. Then we can use this and we using this we can find out u and then using the boundary conditions as I have mentioned, the no slip boundary condition at the wall and the continuity of velocity and shear stress at the gas liquid interface, we can solve it and we can find out ui. But here we need to remember one particular point, that is, for most of the cases we find that usually the liquid film, although it can be laminar, but the gas slug or the gas flow is usually turbulent. So, if that is the case, then what do we do? How do we proceed in that case? For that particular case, a simple semi-analytical solution, it can be formulated by first deriving the equation or the solution for laminar liquid film flow. Okay. Usually liquid flow in film is laminar, but gas flow in core is turbulent. So, for such a situation, what do we do? We find out a simpler semi-analytical solution. For this particular case, it can be formulated how? By first deriving for the laminar liquid film, considering no slip boundary condition at wall, and UL equals to UI at R equals to RTB. Can we not do this? So, therefore, if for the case of laminar liquid flow in the film and turbulent gas flow in the core, the simpler semi-analytical solutions can be formulated by first deriving the expression for laminar liquid film, and the boundary conditions for deriving the expression is no slip boundary condition at the wall, and the liquid film velocity is going to be the interfacial velocity at R equals to RTB. Now, for such a case we find that the liquid velocity profile is obtained by the expression which is given here. Now, once we have derived this, then we go for deriving or for the gas phase in the Taylor bubble region. So, for the gas in the Taylor bubble region, what we do? We can write it down, the momentum balance equation as the Taylor bubble region. This is again interfacial friction. In this particular case, this is the this is the interfacial friction Fi. The way I have told, very sorry, for the gas phase in the Taylor bubble region, I am extremely sorry, the momentum balance equation on the gas core gives mu L du dr at R equals to RTB. This should be RTB by 2 minus dP dz frictional for the Taylor bubble portion, right. We can write it down in this particular way, and then from there we can find out the interfacial velocity from this particular expression and the expression I have shown. We can find out the interfacial velocity as UI is equal to minus 1 by 4L, the pressure gradient in the Taylor bubble region in this particular form. So, therefore, what do we have now? We have the expression for the frictional pressure gradient in the Taylor bubble region, which I had mentioned. This is the frictional pressure gradient in the Taylor bubble region. Here Fi can be derived from this particular expression. For for Ui, we have got this particular expression, right. So, from these three equations, we can solve for the three unknowns which we have. Okay. So, if we know Jg, if we know Jl, if we know alpha, then from here we can find out minus dP dz frictional for the entire unit slug. The only thing which we do not know in this particular case, which we need to find out, is the relative length of the liquid slug and the Taylor bubble. Now, this is often derived by considering the expression of alpha, the void fraction. Usually, we know alpha, it is equal to LTB by LTB plus LLS into RTB square by R square, right. And several experimental investigations have shown that usually RTB by R, it is close to 0.9. Okay. So, therefore, this can easily be substituted in the expression of alpha, and from there one can very well estimate the relative length of the liquid Taylor bubble, and the relative length of the liquid slug is nothing but 1 minus the relative length of the Taylor bubble, as is quite evident, right. So, therefore, this can also be derived, and once this has been derived, then we know all the terms here, we can substitute the terms and find out the frictional pressure gradient for unit cell in the slug flow pattern, and this gives us the frictional pressure gradient for the entire slug flow pattern. Here I would also like to mention that even if we do not consider the value of alpha from experiments, we can find out the value of alpha from several correlations which are available. there are several correlations are also available, from which even without knowing alpha we can find out the relative lengths. And the other thing which I would also like to mention is that if we can either assume this RTB by RO equals to 0.9, or there are several correlations available for the liquid film thickness in terms of the hydraulic diameter as a function of capillary number. Such correlations can also be adopted, and they can also be used to find out RTB by R square, from which the relative length of the Taylor bubble and the liquid slug region can be obtained. So, therefore, this is one particular model which we use for the slug flow pattern, and I would also like to mention that since I had expressed that when we observe the flow pattern in a micro channel, we find that several flow patterns exist at the same time. So, a better model will be if we consider we develop the pressure gradient for the Taylor bubble region, for the liquid slug region, for single phase liquid flow, for single phase gas flow, for the annular flow region, and we also know the relative time of existence of the different patterns, and if we weight each particular pressure gradient with the time of existence of that particular distribution, we would be getting a much more accurate expression of pressure gradient. But in order to do that, we have to know the time of existence of the different flow patterns, and again we have to depend on experiments for this particular evaluation. So, with this I come to an end on the analytical models for the hydrodynamics of gas liquid and vapor liquid flows in microchannels. And at the end, in the last lecture, I would be dealing with some flow boiling aspects in micro and milli channels, and that will be the end of my lecture series on adiabatic two phase flow and flow boiling in microchannels. Thank you very much.